So let's talk about a data structure with a name that sounds, well, almost mean: cuckoo hashing. It's a fantastic example of computer science looking at the animal kingdom and learning a lesson in brutal efficiency.
Okay, so first things first, let's talk about the bird. The cuckoo has this, let's call it a ruthless survival strategy. See, it doesn't bother building its own nest. Instead, it finds another bird's nest, lays its egg, and then the cuckoo chick, once it hatches, often just shoves the original eggs or even the other chicks right out. It's a total takeover.
And that exact brutal efficiency, it turns out to be the perfect inspiration for an algorithm designed to solve one of the most common headaches in programming: hash collisions. When two different pieces of data try to cram themselves into the very same spot in a hash table.
All right, so how on earth does a bird's nasty nesting habits translate into code? Let's break it down.
The core idea is honestly as simple as it is aggressive. When you want to put something new in a spot that's already taken, you don't politely look for another empty spot nearby. Nope. You just kick the old document out and take its place. Now, the evicted element has to go find a new home for itself. Now, to make this whole kick-out strategy actually work, cuckoo hashing had to change the rules of the game right from the start. So instead of your standard one table and one hash function, we're going to use two of each. What that means is every single piece of data now has two potential places it can live: one spot in the first table, calculated by the first hash function, and a completely different spot in the second table, calculated by the second.
And you know what's great about this two-home setup? It makes other stuff incredibly simple. You want to find something? You only ever have to check two spots. That's it. Done. Deleting? Same deal. Find it in one of those two places and poof, it's gone. This guarantees your lookups and deletions are always super fast.
Okay, but here's the million-dollar question, right? What happens when you go to insert a new element and you find that both of its potential homes are already occupied? This is where the real cuckoo strategy kicks in. This leads to something we call the eviction cascade, and it's pretty wild. Let's walk through it. Say we want to insert element X. We try its first spot in table 1, but whoops, Y is already living there. The cuckoo way? Too bad for Y. We just shove X in there and kick Y out. Now, poor Y is homeless and has to find its other home over in table 2. But what if that spot is also full? Well, you guessed it, the element living there gets kicked out and the whole chaotic chain reaction continues.
This really gets to the heart of it, right? It's captured perfectly in our source material here. The algorithm doesn't ask permission, it just acts. It slams the new element in, throws the old one out, and then deals with the consequences. It's aggressive for sure, but it's effective.
So a single tiny insertion can basically set off this domino effect. You get elements bouncing back and forth between the two tables, each one desperately trying to find an empty spot. This whole chain of events has a name: an eviction path. Now, I know what you're thinking. This sounds like pure, uncontrolled chaos. How could we ever predict or manage this? Well, it turns out there's a surprisingly elegant way to see what's really going on. We can actually model this entire system using something called a cuckoo graph. And what this does is it cleverly turns our data structure problem into a graph theory problem, which, believe me, gives us some really powerful tools to work with. So here's how you can picture it. Imagine every single slot in both tables is a dot, a node, and every element we've stored is a line, an edge, connecting its two potential homes. When we insert a new item, we're literally just drawing a new line on the graph. And that crazy eviction cascade we were talking about, in graph language, that's just us walking along those lines, from dot to dot, hoping to find one with nothing attached to it. And this graph model just brilliantly shows us when things work and when they break. An insertion will work out just fine if the eviction path is a simple line, or maybe has one little loop in it. It'll eventually find an empty spot. But, and this is a big but, if adding our new element creates a tangled mess with two or more loops all connected, the eviction process gets trapped. It just bounces back and forth forever, an infinite loop. Okay, hold on. If this thing can literally fail by getting stuck in an infinite loop, how can anyone possibly call this a fast algorithm? I mean, that sounds like a massive, deal-breaking flaw, right? Well, it's not really a flaw, it's more of a calculated risk. And the reason it's so blindingly fast in the real world comes down to a bit of probability, and one really important rule.
And here it is, the golden rule of cuckoo hashing. You absolutely must keep the tables less than half full. You need a lot of breathing room. Why? Well, all the deep mathematical analysis shows that as long as your tables are nice and sparse, way more slots than there are items, the chances of a new element accidentally creating one of those dangerous, tangled, multi-loop structures is just incredibly low. An infinite loop is possible, sure, but in practice, it's super, super rare. So let's just wrap this all up. Lookups, they're always O of 1, which is just CS speak for ridiculously fast, always just 2 checks. Insertions, they are what we call expected O of 1, meaning on average, they're just as fast. Now, what about that worst case scenario, that infinite loop? The system has a safety net. It triggers a rehash, basically tearing everything down and rebuilding it with new hash functions to fix the problem. And the beauty of all this is you get this incredible speed without needing any complex baggage like pointers or linked lists. Cuckoo hashing is just such a cool example of biomimicry in our field, right? Taking a lesson straight from nature's sometimes brutal playbook. And it really leaves you wondering, doesn't it? What other genius strategies from the natural world are just sitting out there, waiting to inspire the next big breakthrough in our code?